Hello everyone. So today we're going to recap the divide and conquer algorithm, and we are going to talk about merge sort. So for the divide and conquer algorithm, as you have seen in the previous lectures, first thing we need a base case where we can solve the problem directly. And it only is possible if the problem size is so small that we can solve the problem directly. Say my array size is 1, if I only have one element, sorting it is straightforward because that element is itself is the result, right? And the next step is we must have a base case. That's the first thing. The second thing is we have to divide the problem into two or more smaller subproblems and recursively then solve the subproblems and finally combine the solutions into the subproblems. So in a divide and conquer sort, our input is A from left index up to the right index. So this is suppose an unsorted array of integers. Our target is to reach a sorted non-decreasing order within the same array. So how do we do that? First, the base case is if I keep on dividing the array until we reach one element, then one element itself is sorted, right? So we return. That's the first thing. And the second thing is we have to do like not this is the first thing. This is a base case. So this is where we start returning. But we start our algorithm by dividing our input into two subarrays, first part and the second part, right? And now our bigger problem is divided into two smaller subproblems. Sort the first part and sort the second part. So we recursively sort the first part, we recursively sort the second part, and then we combine the first part with the second part. So let's talk about merge sort, which uses the divide and conquer method. So the idea of the merge sort is we first divide the input array into two parts, first part and second part. Okay, and then we merge them, and then we recursively sort. So first we divide, that's the first step. Then we recursively sort them, and then we merge them or combine them. Okay, so this is the pseudocode for merge sort. So you're given an input array A, which starts from the left index up to the right index. If at some point the left index crosses the right index, then we return, right? Okay, and then we divide it. So we find the middle. How do we find the middle? We just find the middle point, middle index, because we know the left and right index. And then the array is now divided into two parts, right? So we call merge sort on both the parts. The first part starts from the left index up to the middle index. The second part starts from the middle plus one index up to the right index. So we recursively call the merge sort on the middle and on the left and the right array, like right part, and then we merge them. Okay. So this is the simple recursive algorithm for merge sort. Now, this is the illustration. Like, suppose the green color denotes the sorted first part, the red color denotes the sorted second part, and then we merge them, and this is the ultimately combined merged one. Now you see this is a combination of red and green. The reason is, suppose this part of red was smaller, it went here, right? And then this part went here, and then this part went here, right? And this part went here. So basically, that's why this is looking like this. Now, here is an example of a merge sort. So this is suppose my left part, and this is my sorted right part. So already we have applied the merge sort on the left part on the first part, or left part, and then I have applied merge sort on the second part, and both of them are now sorted. Now this is the important thing. This is a very important. So to merge them, we actually need extra memory to save the values. Otherwise, say if I try to merge them here, like how do I merge them actually? So I want to merge this and this, right? How do I definitely need extra memory. Otherwise, I cannot actually do it, right? I cannot do it in place. Because if you just like swap 1 here and 2 here, then you actually cannot do this. So for that, we need extra memory. How much extra memory you need? You see, if this is the size of the array, we actually need in total n, like n over 2 here, n over 2 here, right? So in total, we need n memory, the same amount of memory. So what do we have to do is we take this extra space, we copy the first part into one of them and the second into one of them, right? And then okay, somehow the animation got messed up. So this should have been gone in here. This should have been gone in here. Okay, so this is where we are, right? Next, we have 2 pointers, both staying at the left of both, like both is staying pointing to the smallest element in both. And then we take the smallest out of these two and put it in, like we are merging actually, right? So one goes here. Now this one moves here because this one is copied. So this one moved. Now we combine 2 and 4. Obviously 2 goes there. So the pointer moves. Now we compare 3 and 4. 3 goes there, and then 7 and 4. So we keep on doing this, right? And now you see that this one goes out of bound. So next what I do is whatever is left here, I just copy it here. Okay, so this is how the merging happens. The important thing is here we needed these extra memory, auxiliary memory, right? So we are done, and this is the code for it. So this is, we create, like, this is the extra memory, and then we copy the first part into the L array and the second part into the right array, right? And then we keep on checking, like we have a pointer I and J, and both of them are actually pointing to the smallest element in the respective parts, right? And I have shown you the illustration, right? So you just keep on comparing and then put it into array A. And at certain point, one of them may get exhausted, so this may become true. Next, what I do is I just, depending on which one is exhausted, I copy the rest of it into the other one. Okay, so in the previous example, you saw that this one is exhausted. Now I just take the rest and copy it here. That's exactly what you are seeing happening here. Okay, so how much time it's taking? So it's taking order of n time. The reason is you see here. So when you are actually merging, you see this one has this one has the size of n1 and this one has the size of n2. And n1 plus n2 is obviously is equals to n. So this one moves in 2 places, right? This one moves in 1 places. So how many moves actually are happening in total is, so total number of moves is n. Okay, so this is total number of moves. So, and how many times we do copy? N times, right? So n copies are happening. So in total, we are doing actually n moves and n copying. So the time complexity is order of n. That's exactly what's being shown here. And space complexity, you saw that in total, we need n extra memory. So this merge part takes order of n space and order of n time. So here is a full example of a merge sort for an input array A starting from index 0 up to index 7. First I divide, okay, and then you see this is the first part. So I have to call merge sort again on this, right? This is, I have to divide again. And then I do divide again. And now I have reached a base case. You see that? I have reached a base case. So I can say now this is sorted. For the second part, this is sorted. Now I have to do a merge, right? And once I do the merge, you see this is sorted. So this is the merge part. For the second part, I again do the divide. And then I'm done. Once I'm done, you see the direction of the array changes, right? Okay, and next, this one is done. So I return it. Okay, now next I have to do a merge of these two. Once I do a merge, they will be sorted. So I do a merge and then I return it. Okay, now you see the merge sort of this part is done. Merge sort of this part is done. Next, I have to do a merge of these two. Okay, so once I do a merge of these two, you see the merge happened and I'm returning it. And now the left part is sorted. Similarly, right part, it will do the same things. And finally, I have to merge this part and this part, right? So if I merge both of these two, like the first part is from 0 to 3, the second part is from 4 to 7. Then the whole thing is merged and I get my sorted array. So what is the time complexity of merge sort? So you see that I kept on dividing, right? And this is where I reach. So each one had one element, right? So after I merged it, they became 2 elements. Then they became 4 elements, and then they kept on going. So how many levels we have from here? So in every level, you see the subproblems have half the amount of size. So it's n, each of them have n, each of them have n over 2. Here, everything has n over 2 square, right? So in total, there are like log n levels. And also you have seen that the merging, so you have seen that the merging takes order of Cn time. I have shown you how the merging takes order of Cn time, right? So here, the merging takes order of Cn time. They're like, each of them takes Cn over 2. So each of them have a size of n over 2. And then there are 2 of them, 1 and 2. So in total, is order of Cn. Here, there are 4 of them, right? And each of them is taking order of Cn over 4. So in order of Cn time. So merging is actually taking order of Cn time in each level. And then we have log n levels. So in total, the complexity is going to be Cn into log n, which is order of n log n. Right? So the total running time is on n log n. And the space in every level, we are using order of n extra memory. We can actually reuse that memory in every space, every level, right? So in total, we need order of n extra memory. So the approach for the merge sort was divide and conquer. And as you can see, most of the work was being done in the merging. The total time was order of n log n, and the space was order of n. And this is like a drawback of merge sort, because all the other sorting algorithms that you have learned so far didn't need this much space. So this one needs like significant extra memory, but the time complexity improves. Okay, so that's it. Thank you very much for watching. We'll come back with the quicksort, which also follows the divide and conquer algorithm in the next lecture.